In this video, we want to take a look at 3 examples of circular motion and forces that cause them. The easiest one to start with is a mass on a string. So this is a view from above and a view from the side. In this case, the centripetal force has got to be inward. If I'm going to do a force, I probably should come up with a mass. And so let's say that the mass is equal to something fairly light, 20 kilograms. Good. So the centripetal force has to be inward, and we have a velocity. And what I did is I specified what the radius is, and then I said how much time it takes to go all the way around. So when we do Newton's second law, we say F net equals ma. Well, with circular motion, remember, this is the cause of forces on the left-hand side, and what the forces are doing, what the object's doing on the right-hand side, and it's doing a circle. So we can automatically say that the acceleration is mv squared over r. So this step is because it's a circle. And the only force that's causing it is tension. So what we might have to do here is find centripetal acceleration and force of tension. But I have to figure out what the speed is first, and I have to utilize this 0.5 seconds. So speed is equal to, well, the oldest way I can do this is just do distance divided by time. The distance is a special distance. It's the distance around a circle divided by a special time, the period. So 2 times pi, and the radius is 2 meters. Divided by the time, and that was given as 0.5 seconds. Lots of 2's in this example. So 2 and pi times 2 divided by 0.5. Okay, so I get 25.1 meters per second. Great. So then the centripetal acceleration is equal to v squared over r. And so I square this, and I divide by the radius, which is 2. Okay, so I get 316 meters per second squared, which is a lot. And sometimes to quantify what a lot is that we could compare that to the acceleration due to gravity, which is 9.8. So this says that the centripetal acceleration is 32.2 times greater than the acceleration due to gravity, or 32.2 G's. And then to finish it off, I can just multiply it by the mass. So I'll just multiply this out. And that means the tension in the string is going to have to be 63 newtons. Okay, good. Now over here, here's a car going around a curve. And so this force is pretty obvious. It's a force due to tension. But in the case of a car going around a curve, we have this view from above, and we have sort of a side view here looking at the headlights. And this force has to come from friction. And what we're supposed to do is find out the maximum safe speed given a coefficient of static friction between the tires and the road of 0.8. Now this is static, even though the car is moving. But with tires, it's always, hopefully, it's always static friction. Kinetic friction happens when you're skidding out of control. So nobody wants that. Okay, well, great. So max safe speed. So we do F net equals ma again, of course. And then the force that's causing the motion is friction. And then that's resulting in circular motion, right? So there's our pattern. Because it's a circle, we automatically write down v squared over a for the acceleration. Now this is a horizontal surface. I mean, many curves are banked, and we could do that example if you want, but it's kind of tedious, and it doesn't really lead to more learning. So force of friction is equal to coefficient of friction times the normal force. And the normal force in this case is just equal to mg because it's on a level surface. So coefficient of friction times m times g equals m v squared over r. And that's how come we didn't put a mass in for the car, because it should work for all cars, right? That would be kind of scary if we had some cars that could make it around the corner and some couldn't. It actually all comes down to the tires and the road condition too. Because if it's an icy curve, then the coefficient of friction is going to drop. And we see frequently people not paying attention to basic physics. So, and having to call it tow truck. So masses on both sides cancel. And so 0.8 times 9.8 is equal to v squared. And then the radius we said is 40 meters. Right, so I can solve for v. What I'll do on my calculator is I'll say, okay, 0.8 times 9.8 times 40. Okay, now I need to take the square root of both sides. So square root times the answer. Okay, 17.7 meters per second is the max safe speed. Anything higher than that, then friction's not going to be able to keep you moving in a circle, and you wind up going in a straight line. And in this last example, sort of the gravitron example, it's an amusement park ride, and it spins so fast that you feel like you're pushed up against the wall, and they can actually pull the floor out from underneath you. Pivot Interactives has a little video of this, which is kind of cute. So I'm going to share that with you right now. And we'll take a look at it. So I'm just going to play the video. And so we see a little doll of Albert Einstein on a board, and this machine is rotating. This is a cell phone right here. And so this wooden platform is rotating. And right now, there we go, he slips down because there wasn't enough friction to hold him up anymore. So that's our example. We want to find out how much force is being exerted. So we have a force of friction. In this case, it's going to be upward. And then gravity is pointing down, of course. And then this now becomes the normal force, which is pushing inward. And of course, these two are connected together. So it's equal to the coefficient of friction times the normal force. So this is an interesting example because it brings up this idea that the normal force is always perpendicular to the supporting surface. But so remember, there's no floor on this, and it needs to spin fast enough. So just the force of friction is going to keep the person from slipping downward. Again, we have the period 2 seconds, and we have the distance. So we can just go ahead and put that in there. So v is equal to 2 pi r over t. And so 2 times pi times the radius I had is 5 meters divided by 2 seconds. Okay, so 15.7 meters per second. Great. So the force of friction has to equal gravity in this case. So the force of friction, which is equal to the coefficient of friction times the normal force, is equal to mass times gravity. Okay, and it's the normal force that's providing this centripetal acceleration. So F net equals ma, one more time. And this is coming from the normal force, but the normal force is equal to, well, let's do this. So m v squared over r. And the normal force is going to equal gravity divided by the coefficient of friction. Okay, and we're actually looking for the coefficient of friction. So in this, right, it doesn't depend on people's masses. And then if I solve for this really quick, I'll just come up here. So 9.8 has to be equal to the coefficient of friction times v squared over r. Okay, well, let's do v squared over r. So v I already have here in the stack on my calculator, and so squared and divided by the 5 meter radius. Okay, 49.3. Okay, and then 9.8 divided by that answer means the coefficient of friction that we need to happen is actually pretty low. So 0.20. Good. All right, so I hope these 3 examples help out a little bit. I'll move my calculator out of the way and then you can just have this for a final shot. Okay, good luck on those homework problems.